Hello. Welcome to another stream. I'm going to be studying Calculus 2 again, but this time I would be learning sequences and series. Let me just set up my chart and then I'll actually start the stream. Last time I learned about first order linear equations. This topic, I think it would be a little simpler. It would be more about discrete math. Okay, let me change to full screen. Okay, so last time we did differential equations and we finished this chapter. This time we are going to do sequences and series. Hold on. Yeah, I was just checking if my mouse was visible. Uh, the topic of infinite series may seem unrelated to differential and integral calculus. In fact, an infinite series whose term involve powers of a variable is a powerful tool that we can use to express functions as infinite polynomials. Okay, it's going to take its time loading. Also, I had other channels. I made a separate channel for language learning. I don't know if I said that last stream. Then one for clips, and then a separate channel for just for proofs. Anyways, terminology of sequences. To work with this new topic, we need some new terms and definitions. First, an infinite sequence is an ordered list of numbers of the form a1, a2, a3, and so on. Each of the numbers in the sequence is called a term. The symbol n is called the index variable for the sequence. We use this notation to denote the sequence. So from n is equal to 1 to infinity. A similar notation is used for sets, but a sequence is an ordered list, whereas a set is not ordered. Okay, let's consider the infinite ordered list 2, 4, 8, 16, 32. This is a sequence in which the first, second, and third term are given by a1 is equal to 2, a2 is equal to 4, and a3 is equal to 8. You can probably see that the terms in this sequence have the following pattern: to the power of 1, to the power of 2, to the power of 3, and so on. Assuming this pattern continues, we can write the nth term in the sequence by the explicit formula 2 to the power of n. Using this notation, we can write the sequence as to the power of n from n is equal to 1 to infinity. Alternatively, we can describe this sequence in a different way. Since each term is twice the previous term, this sequence can be defined recursively by expressing the nth term a n in terms of the previous term a n minus 1. In particular, we can define this as a sequence an where a1 is equal to 2, and for all n is more n which is more than or equal to 2, each term is defined by the recurrence relation. An is equal to 2 an minus 1. An infinite sequence is an ordered list of numbers of the form a1, a2, and so on. Sometimes sequences are defined by explicit formulas, in which case an is equal to f of n for some f of n defined over the positive integers. In other cases, sequences are defined by using a recurrence relation. In a recurrence relation, one term or more of a sequence is given explicitly, and subsequent terms are defined in terms of earlier terms in the sequence. Okay. Note that the index does not have to start at n is equal to 1, but could start with other integers. For example, a sequence given by the explicit formula a n is equal to f of n could start at n is equal to 0. Alright. Two types of sequences occur often and are given special names: arithmetic sequences and geometric sequences. In an arithmetic sequence, the difference between every pair of consecutive terms is the same. For example, consider the sequence 3, 7, 11, 15, 19. You can see that the difference between every consecutive pair of terms is 4. So an arithmetic sequence could be like this. So let's say a is the first term, and then the next term is a plus a difference, and then the next term is a, the previous term plus another difference, plus d plus d. So basically 2d. Whoops. And then a 3d. They're using a n to represent a term, right? This would be a 0. Let me use something else. How should I represent the first term? Alpha, alpha, alpha. Oh no, not alpha. Let's say b. B is the first term. So a particular term is equal to b plus n minus 1d. And then let's say it starts with 1, n is equal to 1. This would be b, n is equal to 2. This would be b, yeah. So the first one is n is equal to 1. And the formula is defined like this. Formula for a particular term in an arithmetic sequence. Arithmetic sequence. Geometric sequence. So for a geometric sequence, you have the first term, and then first term is multiplied by something, let's say r. So you have something like 1, 3, times 3, and then times 3 again, then times 3 again, and times 3 again, like that. So a b, br, br times r, so br squared, and then so on. So a particular term is b to the power of n. N is equal to 1. No, sorry. It's r times n minus 1. R times n minus, assuming that the first term is n is equal to 1. Wait, what did I write in my website? I think I assumed that first term is n is equal to 1, finding a term in an arithmetic sequence. Yeah. In a geometric sequence, the ratio of every pair of consecutive terms is the same. For example, consider the sequence 2 minus 2 over 3, 2 over 9, minus 2 over 27, and so on. We see that the ratio of any term to the preceding term is minus 1 over 3. Assuming this pattern continues, this sequence is a geometric sequence. Finding explicit formulas. Okay, find an explicit formula for the nth term of the sequence. Minus half. So what is it? Minus half 2 over 3 minus 3 over 4 4 over 5 minus 5 over 6. So a to the power of n is so whether it's negative or positive would depend on the whether n is even or odd. So when n is 1, the term would be negative. Then this is 3, 4, 5. We can define it by n itself, right? So n is equal to 1, 1 over 2, a negative 1 over 2, n is equal to 2, 2 over 3, n is equal to 3, negative 3 over 4, n is equal to 4, 4 over 5. Finding explicit formulas. Is this correct? Yes. As for the next one, 3 over 4, 9 over 7, 27 over 10. Okay, so the numerator is multiplying by 3. 4, 7, 10. The denominator, it's adding 3 every time. 3 to the power of n, 3n plus 1. Oh yeah, it's starting with 4, then adding 3 every time. For each of the following recursively defined sequence, find an explicit formula for the sequence. So A1 is equal to 2. And then AN is equal to minus 3 previous term. Minus 3 n minus 1. Minus 3 a of n minus 1. Okay. So this would be 2. And then two times 3 is 6. Then 6 times 3 is 18. But since there is a minus, and then 18 times 3, 54. I have a calculator near me. Minus 54 and so on. So A of n defined by a formula. So it's starting with 2 minus 3 n. If n is 1, if n is 1, we get 2. If n is 2, get 2 minus 3. No, wait. Minus 3 times 2. N is equal to 1. A1 is 2. A2 is negative 3 times 2. A3 is negative 3 times negative 3 times 2. A4 is negative 3 times negative 3 times 2. I think I know. Like this. So an is negative 3 to the power of n minus 1 times 2. So if n is 1, we get 2. If n is 2, we get minus 6. If n is 3, 3 times 3 is, hold on. Yeah, 3 times 3 minus 3 times minus 3 is 9, and then times 2, 18. So A1, let's try the next one. An plus half to the power of n. And I can write it like this. So half and then half plus 1 over 4 plus 1 over 4 and then the previous term plus it with now n is 3 8 and then this 8 times 2 is 16. So let me evaluate this. This would be 3 over 4. 3 over 4 plus 1 over 8 would be 3 times 2 is 6 plus 7. And 7 over 8 plus 1 over 16. 17 times 2 would be 14 plus 1 15. So AN is 1 3 7 15 2 4 8 16. 2 to the power of n and then 2 to the power of n minus 1. Let me see the answer. So this is correct and this is also correct. Limit of a sequence. A fundamental question that arises regarding the infinite sequences is the behavior of the terms as n gets larger. I think for the arithmetic sequence, it's not going to make sense because it's always going to add. It's going to add and add and add, and it won't reach a limit. It'll just keep going to infinity. For geometric sequence, if r is below 1, then the terms are going to get smaller and smaller and smaller. Let's say BR R to the power of x. Let's say the first term is 5 and R is 0.1. First term is 3. Let's do f of x. F of 1 is 0. Yeah, let's do x minus 1 actually. First it's 3, then it's 0.3 because it's 3 times 0.1, and then the next term would be 3 times 0.1 times 0.1. and then it will keep going like this. So as x goes to infinity, the sequence would reach 0. This gets larger and larger, it will get closer and closer to 0. Okay. 1 plus 3n, 4, 7, 10, 13. The terms 1 plus 3n become arbitrarily large as n goes to infinity. Did I write the formula for infinity? Finite terms sum to infinity. Okay. 1 minus half to the power of n. The terms approach 1 as n goes to infinity. Term alternate but do not approach one single value. For minus 1, 1, minus 1, 1, so on. Minus 1 n to the power of n. Minus 1 half minus 1 over 3, 1 over 4. Terms alternate for this sequence as well, but as it goes to infinity, as n goes to infinity, minus 1 to the power of n over n goes to 0. Yeah, they will alternate, but they will converge to 0. A convergent given a sequence an if the terms an become arbitrarily close to a finite number L as n becomes sufficiently large, we say an is a convergent sequence and L is the limit of the sequence. In this case, we write limit as n goes to infinity is L, otherwise it's a divergent sequence. Okay. All right. Limit of a sequence defined by a function. Consider a sequence an such that an is equal to fn for all n greater than or equal to 1. If there exists a real number L such that limit of f of x is equal to L, then an converges and limit of an is L. We can use this theorem to evaluate limit of r to the power of n for where r is between 0 and 1. For example, consider the sequence half to the power of n. Couldn't it work when r is negative maybe? Okay, never mind. Since limit of half f to the power of x is equal to 0, we conclude that the sequence half to the power of n converges and its limit is 0. Algebraic limit laws. Proof of part 3. What do they mean by proof of part 3? Proof of this? Determining convergence and finding limits. Okay, for the first one, the limit is 5 because this part 3 over n square will go to 0. So for this part, um, three n 4 limit 3 n 4 minus 7 n squared plus 5. 6 minus 4 n to the power of 4. Minus 4 minus 7 n squared plus it with 5 n to the power of 4. So if the limit of n goes to infinity, this part will go to 0. So will this and this. You will be left with minus 3 over 4. As for 2 to the power n over n squared, 2 to the power of x squared to the power of n grows larger, right, than n squared. So c will go towards infinity. This is an intermediate form of 1 to the power of infinity. Minus 3 over 4, this diverges n to the power of infinity. So ln Okay, let me see what they did here. L'Hopital's rule. Hold on. Rewrite it as a fraction to apply L'Hopital's rule. Oh, wait, no. Oh, yes, now I understand. Now it is an indeterminate form, 0 over 0. Applying L'Hopital's rule, we get 4. Continuous functions defined on convergence sequences. Consider a sequence A and suppose there exists a real number L such that the sequence A n converges to L. Suppose f is continuous at L, then there exists an integer n such that f is defined at all values A n for n greater than or equal to capital N. And the sequence f a n converges to FL. Wait, I don't understand. Consider this a sequence AN which converges to L. Suppose f is a continuous function at L. Then there exists an integer capital N such that f is defined at all values an for n is equal to greater than equal to n. This sequence f of a and converges to f of f. This 3 over n square if you take n to infinity, 3 over n square goes to 0 and cos 0 is a 1. Start the answer. Squeeze theorem for sequences. Consider sequences an, bn, and cn. Suppose there exists an integer n such that an is less than bn, which is less than cn, for all n which is greater than equal to n, capital N. Then we apply the squeeze theorem. Let me read this. I don't understand what they mean. Then there exists an integer n such that f is defined at all values I think I get it. I think that capital N part confuses me. I think what they're basically saying is, suppose you had for a particular sequence, suppose you had points. I'll make it right here. So for a particular sequence, suppose you had points this, and then the function is something like this. It's going up, and then over here it goes. Over here it goes. And then basically, before it's not defined, there is a function f of x. And then there's this sequence. Before the function, over here the function is not defined for values of a of x, but then later it does. So that means there's a, let's say this, let's draw a dashed line. There's a value capital N such that for all n, for all the values after this capital N, f is defined for the sequence values. F is defined for a of x. That's what it's saying. And then it basically says hold on, no. Defined at all values. No. They're not equal. Sorry, I'm wrong. I am wrong. Wait. Let me put this another way. Yeah. So there is a sequence. So it's like minus, minus, right? And then it starts to converge. But then function f of x f f is undefined for these values of a x. So f of minus 2 is undefined, f of minus 1 is undefined, f of 0 is undefined, and so on. But f is defined for these values of x. Hold on, why is this? Yeah. So after n, the value of f for these, for like 5, 7, 8, and converging 8.1, 8.2, and so on, f is defined. Because when it's converging, we need it to be defined. And if it's converging to L, if it's converging to, hold on. If the sequence is converging to L and f is defined for all of these sequence values, then f of L is um, then f of an converges to f of L, right? Mm, that's how I understand it. Squeeze theorem for series bounded sequences. Sequence n is bounded above if there exists a real number such that n will always be less than equal to m. Bounded below such that m will be the lower bound. On right. 1 to the 1 over n is bounded above because 1 over n is less than or equal to 1 for all positive integers n. It is also bounded below because 1 over n is greater than or equal to 0 for all positive integers n. Wait. Okay. Convergent sequences are bounded. Note that a sequence being bounded is not a sufficient condition for a sequence to converge. For example, the sequence minus 1 to the power of n is bounded, but the sequence diverges because the sequence oscillates between 1 and negative 1 and never approaches a finite number. Consider a bounded sequence an. Suppose the sequence an is increasing. That is a1 less than a2 less than a3. Since the sequence is increasing, the terms are not oscillating. Therefore, there are two possibilities. The sequence could diverge to infinity or it could converge. However, since the sequence is bounded, it is bounded above and the sequence cannot diverge to infinity. We conclude an converges. For example, consider the sequence. Hold on, wait a minute. Suppose the sequence is increasing. Okay, I understand. Since the sequence is increasing and bounded above, it converges. Next, consider the sequence 2, 0, 3, 0, 4, 0, 1, minus, minus. Even though the sequence is not increasing for all values of n, we see that minus half is less than minus 1 over 3, less than minus 1 over 4. Therefore, starting with the 8th term, minus half, the sequence is increasing. In this case, we say the sequence is eventually increasing. Since the sequence is bounded above, it converges. It is also true that if a sequence is decreasing or eventually decreasing and bounded below, it also converges. Okay. sequence is increasing for all n greater than or equal to n naught if the previous term is less than or equal to the next term for all n greater than or equal to n naught. A sequence is decreasing for all n greater than or equal to n naught if the previous term is increasing or equal to the next term. A sequence is monotone for all n equal to or greater than n naught if it is increasing for all n greater than or equal to n naught or decreasing. So if it is one of these, it is monotone. If an is a bounded sequence and there exists a positive integer n naught such that an is monotone for all n greater than or equal to n naught, then an converges. The proof of this theorem is beyond the scope of this text. Instead, we provide a graph to show intuitively why this theorem makes sense. But isn't this trivial? Because if there's a bound and it's always increasing, like if there's a bound and it's monotone, then it's always then it's increasing or decreasing, right? Then it has to converge. Okay, let's do. How many chapters are there? Infinite series comparison test. Okay. Whoops. An infinite series is a sum of infinitely many terms and is written in the form a1 plus a2 plus a3 and so on. A partial sum of an infinite series is a finite sum of the form a1 plus a2 plus a3 to ak. This here is a geometric series, geometric sequence. One plus half. We are interested in what happens as k goes to infinity. Okay. So this to infinity, half to the power of n minus 1. The sum to infinity is 2. An infinite series is an expression of a1, a2, a3 and so on. For each positive integer k, the sum sk is called the kth partial sum of the infinite series. So I just want to remember one thing. So let's say sk b, let's say it's a sum of an arithmetic series. So b and then b plus d and then b plus 2d, and then b plus k minus 1d. If I write this in reverse, I get b plus k minus 1 d plus b. If I add them, I get 2k, but I don't know where I was going with this. No, wait. Yeah, 2b plus k minus 1 d. So if I add the first and last, get 2b plus k minus 1 d. If I add the second plus second last, get b plus d. So 2b plus d plus k minus 2d, but I can just write it as k minus 1d. So d plus k minus 2d gives k minus 1d. And then third term plus the third last term, d2d 2b plus b, right? And then 2d plus, it's not here, k minus 3d. If you add them, you get k minus 1d. So since there are k terms like this, all this will repeat k times. So k times k minus 1d. So then the sum of the partial terms is k over 2 2b plus k minus 1 d. So it's basically the first and last term, k times, and then divided by 2. Let me see, sum of an arithmetic series. Okay, as for the geometric series, sk is equal to br plus br squared. No, wait. B plus it with br k minus 1. and then R times sk gives PR plus PR squared plus it with PRK, and then RK minus SK. So now wait, hold on. Think it should be SK minus RSK. So B plus PR squared, all of this minus this. So BR will cancel out, BR square will cancel out, BR cubed will cancel out, all the way till BR K minus 1 will cancel out. Then we are left with B plus B R to the power of K. And then I can extract SK out. And then 1 plus R to the power of K. So then that means SK is equal to, no, sorry, this is minus. Yeah, this is correct. First term minus times it by 1 minus the ratio to the power of K over 1 over R. Now let's say this is convergent. Each term is convergent, getting smaller and smaller. That only happens when R is less than 1. If K goes to infinity and R I think between minus 1 also makes sense. Between minus 1 and 1, then S is equal to the sum to infinity is equal to S to the power of K. B is a constant, 1 minus if K goes to infinity, since R is between minus 1 and 1, then R to the power of K will go to 0. Right? So then S is equal to, so the sum to infinity is this. Let me check sum of a geometric series of finite terms. Okay. And that's the same answer as this one. You just multiply both sides by, oh, you just multiply top and bottom by minus 1. And then sum to infinity. A over 1 minus R. Okay. For each positive integer k, the sum is called the kth partial sum of the infinite series. Partial sums form a sequence Sk if the sequence of the partial sums converge to a real number S. The infinite series converges. If we can describe the convergence of a series to S, we call S the sum of the series. And we write 1 to infinity is equal to S. If the sequence of partial sums diverges, we have the divergence of a series. So n over n plus 1 is over here. Whoops. N over n plus 1. So 1 over 2 plus it with 2 over 3. Wait, in order for a sum to converge, the term has to go to 0 when n tends to infinity, right? I don't think it says here. I don't think this would. I don't think the sum of this would go to a finite number. Yeah, I don't think so. Okay, so let's say if it's n plus 1 over n plus 1, that's just 1. 1 plus 1 plus 1 plus 1 till forever. That goes to infinity. Minus 1 to the power of n. This is undefined. Let's try this one. The sum to infinity, this time it's 0. N times n plus 1. So 1 times 2 is 2. 2 times 3 is 6. 3 times 4. 4 times 5. So it start off as half. Wait, 1 times 2, 2 times 3, 3 times 4. You can write this as n squared plus n, right? So n squared plus n, 1 plus 1, 2 squared plus 2, 3 squared plus 3, 4 squared. Oh yeah, that makes sense. Anyways, let me think. This isn't exactly a geometric series. The next term would be what? This is 4 times 5, right? I have no clue. We just have to figure out whether it converges or diverges. So it converges, that's correct, but I want to know what the final value is. You can see that the kth partial sum is given by the explicit formula k over k plus 1. So it converges to 1. Useful series to know about is the harmonic series. I know this one. Harmonic series H is equal to 1 plus half plus 1 over 3. And so on infinitely. It looks like it converges, but it actually diverges. If I um let me see how I should show this. Yeah, this one, instead of writing 1, I will write half plus half, and then 1 4 plus 1 4 plus 1 6 plus 1 6, and so on. So this is h1, this is h2. Half plus half, plus it with 1 4 plus it with 1 6 plus 1 6, so on. These new terms, like before it was 1 plus half, now it's half plus half. The changed terms are lesser than the terms over here. So h2 is lesser than h1. Or if somehow both their series converges, let's just start this. So now we can write h2 as one plus half plus 1/3 plus it with, and next one would be 1/8 plus 1/8. I don't think it's equal. 1, so on. Now over here, now h1 is equal to h2. This is a contradiction. Harmonic series. The terms in red is smaller than the corresponding term of h. So h is 1 plus half plus 1/3, and the corresponding term is changed to 1/4, 1/6, 1/8, and so on. Let's group the like terms together. So group the like terms together, and then we are left with half plus 1/3 plus 1/4 plus 1/5. Then since all this is equal to h, there's a contradiction over here. However, I think this proof is wrong, so I need to make some changes. Yeah, I should group this one together. Instead of h, I should write h minus 1. And then we would be left with half plus h, which would be a contradiction. Algebraic properties of convergent series. Oh yeah, we could split the addition. That makes sense. And you can take the constant out. Use algebraic properties of convergent series. So this and this would be handled separately. Okay, I need to make changes for the harmonic series one. Anyways, sum of the first n. Also, I need to prove that n over n times n plus 1, it converges to 1. Now they're introducing a geometric series. Yeah, I explained all this. Determining convergence or divergence of a geometric series. This one diverges. This over here. Let me check. Infinity n is equal to 1. For it is this. This is. So let's start with 1. Minus 3 times minus 3 is 9. It's negative 1. Plus it with minus 27. Plus it with 4. 1, 2, 3. 81. I'm using a calculator. 16. So it's starting with 9 over 1. Then it's multiplying by negative 3 over 4. Right? So the sum to infinity is a 1 minus minus 3 over 4. Okay, I'm using a calculator, so let me check. 5.14. Yes. Writing repeating decimals as a fraction of integers. Use a geometric series to write 3.262626 as a fraction of integers. So three point two six hold on, 3.26 times it by 100 is 326.26. Wait, there was a method of finding this. Let me see if I can remember it. I don't think I remember. Okay, anyways, let's just use a geometric series. So use a geometric series to write 3.26 as a fraction of integers. And let me think about this. 3 plus it with um 26 plus it with 0.26 plus it with 0.00 and so on. So the first term a1 is equal to 0.26, then r is equal to 1/100. Then r, so a1 plus r squared. So then s is equal to 0.26 1 minus r, which is then I can write this as 26/100 1 minus 0.1 minus 26 looks like it can be divided by 3. I don't know why I thought that. So anyways, this, and then 3 plus 20. So the 26 over 99 is basically 0.262626 so on. Wait, hold on. Is that for, let's say, 37 over 99? Oh, that works for any two-digit number. So if I do 3 plus 26 over 9, I get 3 times 99. 99 plus 26, which is 323 over 99. Three two three also looks like it can be divided by 3, but it can't. Okay, is this the solution? It's a fraction of integers. 323 divided by 99. Telescoping series. Consider this series 1 over n times n plus 1. We discussed this series in example 5.7, showing that the series converges by writing out the first several partial sums s1, s2 to s6, noticing that they are all of the form k over k plus 1. Here we use a different technique to show that this series converges. By using partial fractions, we can write 1 over n times n plus 1 is equal to 1 over n minus 1 over n plus 1. Therefore, the series can be written as 1 over, or we can add them separately. Or maybe not. One over n. But the thing is, this 1 over n plus 1 will cancel out with the next 1 over n. So if it's like 1 over 1 minus 1 over 2, then the next series would be 1 over 2 minus 1 over 3. So the 1 over 2 cancels out. If you take this to infinity, we are left with a 1. So the only terms that don't cancel out is 1 and 1 over k plus 1. If we are taking the sum to k. If we are taking it to infinity, we are just left with 1. Hold on. Why is it k over k plus 1? No, I guess k plus 1 over k plus 1 and then subtract. Okay, that makes sense. A telescoping series is a series in which most of the terms cancel in each of the partial sums, leaving only some of the first terms. some of the last terms. We're going back to the harmonic series. I want to check something. Oh, they used a different proof. So 1 over 4 plus 1 over 8 plus 1 over 8 plus 1 over 8 plus 1 over 8. Then you get left with 1 plus half plus half plus half. Evaluating a telescoping series. Determine whether the telescoping series converges or diverges. If it converges, find its sum. This is n, looks like h. Cos 1 over n minus cos 1 over 1 plus minus cos. So sum till k is equal to cos 1 minus cos half plus cos half minus cos 1 over 3, and then all of them until, and then all of them until cos k minus 1 minus cos 1 over, no, still k, right? So 1 over k, and then next one is k plus 1. So the ones in between will cancel out, and then we are left with cos 1 minus it with cos k plus 1. But if k tends to infinity, then 1 over k plus 1 will go towards 0. Then cos 0 is 1. Cos 1 minus 1. Yes. Euler's constant. Should I do the next chapter, or should I just end it here? Okay. I'll just end it here then. Okay, then I guess I'll see you guys later. So I'll continue this topic tomorrow. No, not tomorrow. Next time. Whenever that would be.